Okay, glassboard time, jazz hands. What are we trying to do here, live?
So our program measures this half cycle time. We want to know if that's, it's giving the right value for what's happening in our system.
Right, and so we're given one hint to try to understand what the cycle time is or should be, and that is omega equals. Do you remember what it is?
So we had omega equals the square root of the spring constant k over m.
And what is omega here?
So omega is kind of giving the oscillation speed or angular frequency in terms of radians per second.
That's right. By the way, this is omega. It's not a W. Everybody
Yes.
thinks it's a W. I mess it up sometimes.
The curve in your
Know your Greek letters. Very
Yeah.
important. So what do we know about things that oscillate that we can relate this to, say, the frequency and the period?
Yeah, so if we're talking about something in radians per second, we can relate that to the time or frequency of the cycle or the full oscillation. So if a full cycle is 2 pi radians, then the frequency of that oscillation is given by omega over 2 pi. So this would represent like the cycles per second.
That's right. So so now that we have the cycles per second, and by the way, typically we think about making an oscillation when things are, like circular things are rotating. Nothing's really rotating here, but it turns out that all this math is relevant to that, because at the end of the day there's some angle that goes into a sine or a cosine function, and that angle is going to be in radians. And so it still makes sense to think about it this way, even though all it is this spring going back and forth. All right, so we have the cycles per second. How do we relate that to the period? And by the way, the period is the number of seconds for each cycle, right? So that sounds a lot like 1 over the frequency.
Yeah, so we just flip it.
And so let's see if we can relate the period to this omega, because we know what omega is. Omega is square root of k over m.
Yeah, so if we just put this in here for f, we have omega over 2 pi. I can multiply top and bottom by 2 pi and get 2 pi over omega. And then finally substitute our original hint. Let's simplify that further so we don't have fraction on the bottom.
Yeah, so this is the well-chosen one. So something divided by that same thing is 1. So you can multiply anything you want by 1, and it's still a fair game, right?
Yeah. Okay, so I have this square root of m on the bottom here. It's going to cancel when I put it there. And I get 2 pi, and I'll just slide this square root of k back under the square root here. So it's square root of m over k.
There you go. And just make it clear, this is the period
Yes,
t
it's
there.
still our period, yep.
Okay, so now we've been able to figure out how the period relates to the mass and the k constant, which we know both of those things in our program, right? So now we have to figure out what the trickery is behind this half cycle time thing.
Right.
Okay, and basically what's happening there is that, so let's say that we have some plot of the position of the blob as a function of time. Sorry, time, not x. It's time. And so this is x blob here, and we're going to crash into it. And maybe what I'll do is I'll make this x blob minus L relaxed. And so we're going to crash into it, and it's going to, let's say it's going to compress the spring, right? and then the spring's going to push back until it comes back to this equilibrium length, and then it's going to keep on going. It's going to stretch out, go the opposite way, and then the spring force is going to bring it back until it's here. Now in our program, when is it going to measure the half cycle time? It's like when you remember that counter that's in the code. By the way, this would be like a negative sine function, negative sine omega t. So all right, so we're gonna crash into the thing. We're gonna compress the spring, right? So this is gonna get negative because this is less than that. And then I come back. And then what does the program do then? Does it reset the counter here, or does it reset the counter there?
It resets the counter every time it crosses through.
That's right.
The equilibrium position.
So it resets it here and here and here, right? But what is the period though? What would be the full period though? Is this the full period, or is that the full period, or what is it?
So the full period would be you start someplace and you make the full range of motion before coming back.
Right. So
The place you started.
So if that's true, then t half, the half cycle time, is what fraction of the period?
Big T over 2.
Right. So if this is the period, maybe we could use the orange one. You're gonna draw that on there.
So that's the period.
Yeah. So I'm going to mark that as the full period. Then this is t half. Right. And then this is also t half. Okay, so this is just big T over 2, right? This is the period. So what do we got to do to figure out our half cycle time?
Just divide by 2. So we have so that cancels. We just have pi times square root of m over k.
There you go. So that's our t half. So let's stick this in a calculator and see if it matches up with what's in our program. Nice job.